Here's a number that should genuinely disturb you. In some of the most advanced multi-agent AI frameworks being used in software engineering right now, systems where teams of specialized AI agents collaborate to build entire software products, researchers measured token duplication rates of up to 86%. 86! That means nearly 9 out of every 10 units of computational effort these systems expend are pure waste. Agents endlessly resending the same context to each other, replanning work that was already planned, ping-ponging identical information in loops while the compute bill climbs. But that stat, staggering as it is actually not the most important thing I'm going to tell you today. The most important thing is this. As AI systems become more autonomous in software engineering, as they go from helping you autocomplete a line to writing whole functions to planning and executing entire features without a human in the loop, the amount of human judgment required goes up, not down, up. More AI autonomy, more human judgment required. That is the counterintuitive reality at the heart of everything happening in this industry right now. And if you don't understand why that's true, you are going to be making the wrong bets as an engineer, as a leader, as an investor, as anyone who builds or funds or hires in tech. That's what today's episode is about. Welcome to Mindcast. I'm Will. This is the show that takes the big ideas reshaping our world and makes them genuinely understandable. Not watered down, but actually digested in a way that gives you a real framework for thinking about what's coming. Today, we are going deep on agentic AI and software engineering, not the surface-level AI helps developers code faster conversation you've already heard. We are talking about AI systems that plan, that reason across multi-step horizons, that execute entire features autonomously, and what it actually takes, organizationally, technically, and humanly, to harness that power without it destroying you. One important note. The source research behind today's episode is not publicly available. This isn't something you can find with a search. I've gone into cutting-edge academic and industry research so you don't have to, and I'm bringing you the sharpest insights from it. Here is my promise. By the end of this episode, you'll have a clear mental model of why agentic AI demands a complete reinvention of software engineering. Not just faster tools, but new frameworks, new artifacts, new human skills. You'll understand the specific failure modes that are already taking down real teams, and you'll leave with 3 concrete things you can act on right now. Let's go. Key Insight 1. And this one requires us to go back 57 years to understand what's happening today. October 1968. A NATO conference in Garmisch, Germany, a room full of the most serious programmers and academics alive. And the mood is not triumphant, it's alarmed. Hardware had just taken a massive leap. Computers were becoming dramatically more powerful, fast, and the methods humans were using to program those machines, informal, ad hoc, just figure it out as you go, had completely buckled under the scale of what the machines could now do. Projects were failing. Budgets were exploding. Code bases built for critical infrastructure, hospitals, banks, defense systems were collapsing. Nobody could maintain them. Nobody could extend them. Edsger Dijkstra, one of the titans of computer science, captured the problem precisely. When computers were weak, he said, programming was a mild problem. But gigantic computers created an equally gigantic problem. They called it the software crisis. And the industry's response was to invent software engineering as a formal discipline from the ground up. Structured programming, version control, object-oriented design, formal requirements analysis, standardized development life cycles. All of it built in direct response to that 1968 crisis. Then, nearly 20 years later, Frederick Brooks published the essay that would define the field's philosophy for the next 40 years. He called it No Silver Bullet. And the central idea is something you need to carry through the rest of this episode. Brooks said software development contains 2 fundamentally different kinds of complexity. He called the first accidental complexity. This is the friction of the craft itself. Writing syntax, managing language quirks, dealing with hardware, navigating tooling. Tedious, time-consuming, but in principle, fixable with better tools. The second kind he called essential complexity. This is the irreducible difficulty of the problem itself, understanding what the business actually needs, designing architecture that will hold up as the system grows, managing the long-term coherence of something that evolves over years. This complexity lives in the problem, not the tools. And Brooks's thesis was clear. No technology would ever deliver an order of magnitude productivity leap because every tool only ever attacks accidental complexity. Essential complexity is permanent and inescapable. For 40 years, through high-level languages, cloud computing, microservices, containerization, Brooks was right. Every advance chipped away at accidental complexity. Essential complexity sat there, patient and immovable, until Agentic AI arrived. And here is the revelation. Agentic AI, systems capable of multi-step reasoning, autonomous tool use, long-horizon planning, goal-level execution, is the first technology in history to crush accidental complexity to near zero. Writing syntax? Done. Generating boilerplate? Done. Configuring test scaffolding, drafting documentation, producing first implementations of entire features, all handled at machine speed. But we haven't escaped complexity, we've relocated it. Every ounce of friction that used to be spread across weeks of implementation now compresses directly into the domain of essential complexity. The bottleneck is no longer typing code. The bottleneck is now the judgment required to specify intent precisely, to maintain architectural coherence, to verify that what the autonomous system produced is actually what you meant. The question engineers used to ask, can we build this? Agentic AI has made that trivially answerable. The new question, the harder one, is should we build this? And how do we rigorously prove that the machine built exactly what we intended? Robert Balzer predicted this in 1985. Automate lower-level compilation, he said, and you just move the cognitive bottleneck upward to higher-order specification. We don't eliminate complexity, we push it to harder, more abstract, more consequential problems. And this is exactly why forcing agentic AI into the legacy processes that were designed to manage the human labor of typing code is not just inefficient, it's a structural mismatch that invites systemic failure. Key insight 2. And this is where I need to introduce you to the trap that is currently swallowing entire engineering teams. When AI can generate working code from a casual description in natural language, the instinct is obvious. Just describe what you want and accept the output. Move fast, ship fast, iterate fast. This approach even got a name, vibe coding. And it works in the short run in a very seductive way. You describe an idea, the AI generates a prototype in minutes, a bug appears, you paste the error back into the chat, the AI fixes it. You don't read the generated code deeply, you don't need to, it seems to work. You describe the next feature, more code appears, you accept it, you're shipping at speeds you never imagined. 3 months later, everything stops. The accumulated technical debt, undocumented dependencies, and incoherent architecture compound into a maintenance overhead that paralyzes further development. You literally cannot add new features without breaking existing ones. Scaling is impossible. Security auditing is impossible. The underlying codebase has grown into something no human and eventually no AI can coherently reason about. A tangled web of disconnected AI generations with no coherent structure underneath any of it. This is the 3-month wall, and it's empirically documented. Vibe coding succeeds in the short term by ignoring essential complexity. It pays a catastrophic long-term price. So what does sustainable agentic engineering actually look like? The industry is pivoting hard towards something called spec-driven development, SDD, and the philosophy is the near opposite of vibe coding. Before any AI generates a single line of code, the engineer invests significant deliberate effort in formal specifications, comprehensive machine-readable constraints that define what the AI is permitted to build before execution begins. These specs are the immutable source of truth. This leads into a framework called SACE, Structured Agentic Software Engineering. And SACE makes a structural insight that changes how you think about the whole problem. Humans and AI agents need fundamentally different working environments. Mixing them carelessly degrades both. SACE splits the development environment into two distinct planes. The first is the Agent Command Environment, the ACE. This is the human's strategic cockpit. From here, the engineer defines objectives, assembles teams of specialized agents, orchestrates complex workflows, and reviews evidence of success. Crucially, the ACE presents high-level observability metrics and outcome evidence, not raw code. The human operates at the level of mission and judgment. The second plane is the Agent Execution Environment, the AEE. This is the machine's domain, high-speed, massively parallelized, tireless. Agents interact with compilers, linters, APIs, and each other, and when an agent hits a genuine architectural ambiguity it cannot resolve alone, it escalates automatically to the human in the ACE. The system knows where machine authority ends. SACE also introduces 4 new artifacts that replace the Agile documents that were never built for AI. The briefing script replaces the vague user story, a dense, machine-readable mission brief that eliminates ambiguity before execution begins. The loop script is a dynamic workflow playbook specifying exactly how multiple agents coordinate and cross-verify each other's work. The mentor script codifies your organization's specific norms and architectural principles. Without it, AI generates generic internet average solutions that don't match your standards. And the Merge Readiness Pack, the MRP, completely reinvents code review. Instead of a human trying to parse 10,000 lines of AI-generated code, the agents compile a cryptographic bundle of proof. The code works, it cleared security scans, it passes every test scenario, it conforms to the Mento script. The human reviews the evidence of correctness, not the syntax. And this reshapes the entire development timeline. Empirical studies show AI compresses implementation from weeks to hours, a 55.8% productivity boost and over 70% improvement in early bug detection. Researchers describe this through what they call the V-bounce model. In the traditional development lifecycle, time was spread roughly evenly across requirements, design, coding, and testing. In the AI-native world, the coding phase collapses almost instantaneously, and the project bounces immediately back up into human validation and strategic review. The engineer is no longer a primary implementer. They are a strategic verifier. That is a different identity and a more demanding one. Key insight 3, and this is where the stakes get genuinely high. So far, we've mostly been talking about single agents, one AI system working under human governance. But the frontier everyone is racing toward is multi-agent systems, virtual software organizations where specialized AI agents collaborate. A CTO agent designs the architecture, developer agents implement features in parallel, a QA agent verifies outputs. They communicate by passing messages to each other, cross-checking work, coordinating at machine speed. The research shows multi-agent systems genuinely outperform single agents on complex tasks. The cooperative structure helps each agent overcome the contextual limitations that make any individual model unreliable on large problems. But multi-agent systems introduce failure modes that legacy software testing is completely unequipped to detect, and 3 of them are particularly dangerous. The first, cascading hallucinations. Think of a telephone game where every participant is supremely confident in what they heard. The CTO agent makes one subtly wrong architectural assumption, not obviously wrong, subtly. It passes that assumption to the developer agents as ground truth. They build on it. They pass their work to the QA agent, which validates code that is internally consistent but built on a false foundation. Through iteration loops, that small misassumption solidifies into system-wide false consensus. By the time the failure becomes visible, tracing it back to the original bad assumption has become nearly impossible.
The second, consensus inertia. Once a false belief locks into a multi-agent network, the system actively resists correction. Researchers demonstrated that injecting a single tiny error seed into a collaboration architecture can cause untraceable failure across an entire software build, because every agent keeps confirming every other agent's flawed logic. The network becomes collectively, confidently wrong. The third, and here's that number from the open, token duplication. Up to 86% waste in some frameworks. Agents constantly resharing context they already have, replanning decisions already made. The financial cost is significant, but the reliability cost is worse. It degrades system performance, exhausts API rate limits, and causes production deployments to buckle under load. Here's what makes it chilling. An individual AI agent running at 92% accuracy sounds impressive in isolation, but in a networked multi-agent system, compounding errors across interdependent agents can cause catastrophic systemic failure. Individual accuracy doesn't predict system reliability. Architecture does. Now zoom out to the human dimension, because all of this has profound implications for what it means to be an engineer in this era. A comprehensive 2026 systematic review of the literature produced a 9-dimension competency model built around 3 pillars: intent, collaboration, and verification. The 9 dimensions cover specifying intent precisely enough for machines to execute without hallucinating, critically evaluating AI output rather than accepting it, rigorous verification through cryptographic proof rather than casual observation, metacognition, actively monitoring your own sense of competence, orchestrating multi-agent systems, maintaining foundational computer science knowledge, security and ethics, bridging human stakeholders and autonomous agents, and continuous learning as the landscape evolves. And the research identifies 3 paradoxes that define this era. The productivity paradox: raw code velocity increases dramatically with AI, but the hidden costs of architectural debugging and verification often slow complex task completion. AI magnifies your process quality. Good process gets faster, bad process produces failures faster. The competence paradox: AI creates a dangerous illusion of expertise, especially for junior developers who feel highly productive while having no genuine understanding of the systems they're deploying. Feeling productive and being competent are not the same thing. And the trust paradox: as AI adoption grows, blind trust in AI systems must fall proportionally. More automation requires more rigorous human oversight, not less. That is the inversion most people get completely backwards. Who wins in this new landscape? Organizations that invest in specification discipline, that govern multi-agent systems with real rigor, that cultivate these 9 competencies. Who gets left behind? Teams that mistake vibe coding speed for sustainable engineering. 3 takeaways. Concrete, actionable, starting now. Takeaway 1. Make specification discipline non-negotiable. If your team is using AI coding tools, any of them, ask one question: where do the formal specifications live before any AI generation begins? If the answer is a vague Jira ticket, a verbal description, or a chat message, you have a vibe coding problem in waiting. The fix is not bureaucracy, it's precision. Invest in structured, machine-readable specs that define exactly what the AI is and isn't allowed to build. That investment is what separates teams that sustain velocity from teams that hit the 3-month wall. Takeaway 2. Match your review process to your autonomy level. There's a spectrum of AI autonomy in software engineering, from basic autocomplete all the way to goal agentic systems that plan and execute entire features independently. Most teams are deploying high autonomy AI while reviewing outputs with low autonomy processes. A human trying to manually read 10,000 lines of machine-generated code isn't doing a code review, they're doing theater. If your AI is operating at high autonomy, your review process needs cryptographic proof of correctness, not line-by-line inspection. Build or adopt the merge readiness pack model. The governance has to match the capability. Takeaway 3. Protect and invest in foundational human skills. The engineers who will matter most in the agentic era are not the ones who can prompt AI most fluently. That skill will commoditize fast. The ones who will matter are the ones who can reason about systems independently, catch what the AI gets subtly wrong, and maintain genuine architectural judgment that doesn't depend on the machine's scaffolding. foundational computer science, critical evaluation of AI output, metacognition, the habit of honestly asking yourself whether you actually understand what just got built or whether you're borrowing the AI's confidence. These are not soft extras, they are the irreplaceable core. Let me close with what I think is the sentence that holds all of this together. The engineer of the future is not a typist. They are an orchestrator of immense, autonomous cognitive labor. What's happening right now is not AI replacing engineers, it's the nature of engineering itself transforming, from a craft dominated by implementation to a discipline defined by intent, judgment, and verification. The machines handle the what, the humans are responsible for the why, the whether, and the proof that it was done right. Frederick Brooks told us there was no silver bullet. He was right, but even he couldn't have predicted that the most powerful technology in the field's history would vindicate his thesis by relocating complexity rather than eliminating it. We are in the second software crisis. The first one, in 1968, forced the invention of software engineering itself. This one demands a reinvention. The tools exist, the frameworks are being built. The question is whether the humans inside our organizations are developing the judgment to use them wisely. That is the work of this moment. Thank you for spending this time on Mindcast. If this episode gave you something useful, a new frame, a question worth asking your team, a reason to change something, please subscribe and share it with someone who needs to hear it. That's genuinely how this show grows, and I'm grateful for every person who passes it along. One note on the research. The source material behind this episode is not publicly available as a single document, but I've compiled context, key frameworks, and reading pointers in the show notes. If you want to go deeper, that's where to start. Next episode, we're turning the camera from the technical dimension to the organizational one. What does a company actually look like when it's built natively for this era? What roles change? What new roles emerge? And what does leadership mean when your team includes autonomous AI agents? I think you'll find it worth your time. I'm Will. This is Mindcast.
See you next time.